Okay, so here we have a problem that is a trapezoidal channel flowing into a rectangular culvert, and we're asked to find a multitude of things here. And let's get started. So we're given all the geometry of the channel and of the box, and for starters we're asked to find the discharge. So I've written all the equations that we're going to need for this problem over here. As you can see, this is a pretty in-depth problem. It uses a lot of different concepts. So let's get started. To find the discharge, we know that we're given Manning's in right here. So boom, we know that we're supposed to use Manning's equation. So I'm going to draw a line here and copy Manning's equation back down here. So we have Q equals 1.49 over Manning's in times the area of the uniform section over the wetted perimeter of the uniform section, and the area is to the 5/3 and the wetted perimeter is to the 2/3. Yep, that's correct. Times the square root of the bed slope. And in order to use Manning's equation, we need to find the area and the wetted perimeter of the uniform section. And in our problem statement, we're given here that water flows uniformly in the trapezoidal channel. So that means all the way up until this point here, we have uniform flow. Well, actually, it would be up until here. We have uniform flow. So we need to find the area, which I've written the equation of the area of a trapezoidal channel here and the wetted perimeter here. And this is the geometrical significance of each of these different values. So we're going to write that down here. The area is equal to by plus my squared. And in the problem, we know that b is the width of the bottom of the channel, which we're given in the problem is 25 feet. So we have 25, and then we know the uniform flow depth is here, 13 feet. We're given that, so times 13 plus m in this problem is given as 2 right there. So we have 2, and again times the 13 squared. And I'll calculate that in a minute. And then we move on to the wetted perimeter. And this equation is b plus 2y times the square root of m squared plus 1. And again, if we just enter all these values into the equation, we have 25 plus 2 times 13 times the square root of 2 squared plus 1. And I'm going to pause this and calculate these values. Okay, we have these calculated now, and they are 663 feet squared and 83.14 feet for the area and the wetted perimeter of the uniform section. Now that we have those values, we can simply plug them into Manning's equation. We have 1.49 over Manning's in, which in this problem is 0.030, times the area, which is 663 to the 5/3 power, over the wetted perimeter, which is 83.14 to the 2/3 power, and that is multiplied times the bed slope, which in this problem is given as 0.0005. And if you calculate that all out, just plug that all into your calculator, you get 2,940 CFS approximately. So there we go. There's part 1 completed, or part A completed. Now, moving on to part B, we are given that the entrance loss flowing into the culvert is 0.5, and we're trying to find the minimum width of the box culvert so that there is no choke, which means there's no upstream flooding, and we're to assume inlet control. And inlet control just means that at section 2, or like right when we hit the culvert, that means that that is the critical depth. So we initially need to find the specific energy of the uniform section, and we can do that by the specific energy equation, which is y naught plus q squared over 2g a naught squared. If we just plug those values in, we have 13 for y naught plus q squared is 2940 squared over 2 times 32.2 times the area, which was 663 squared. And if we calculate that, we get 13.3 feet, or yeah, 30 feet. That's the specific energy at the uniform section, which in this problem is section 1, is anywhere back here. The specific energy is 13.3 feet. Now, we're going to use a separate version of the specific energy equation here, and I've written that right here. And this is specifically used for a culvert of any geometry flowing into a rectangular culvert. And it has to be flowing into a rectangular culvert in order to use this equation. So I'm going to copy that back down here. We have E1 is equal to 1.5 plus the entrance loss over 2, all that times Y2 critical, and then plus delta Z. In this equation, delta Z is simply the bed drop or the bed rise. So if this diagram right here were to go, would to slope down or would to go up, then we would have a delta Z value. But for this problem in particular, we don't have that. So we can just get rid of that. We don't need that for this part. And if you recall what I said, the uniform flow or the uniform specific energy is equal to the section 1 specific energy, since section 1 is uniform flow. And this is pretty simple. We just plug these values in because we have the specific energy given here. So we have 13.30 is equal to 1.5 plus the loss coefficient, which in this problem was given as 0.5, and all that times Y2 critical. And you just solve that for Y2 critical, and we get a value of 8.74 feet. Okay, and again, 0.5 entrance loss is given in part B's question. Now that we have Y2 critical, we can we have the Froude number equation somewhere right here. So Froude number equals 1 because at section 2 right here it's under inlet control, which means section 2 is at critical depth. So we know at the critical depth the Froude number equals 1, which means that all this under the square root right here is equal to 1. And if we do some rearranging of that equation, we can find that the unit discharge is equal to the square root of g times the critical depth cubed. And that's just simple, just algebra manipulation. So if we come down here and we copy that down here, we have q equals whatever that says, square root of gy critical cubed. And since we have y critical and we know g, we can calculate that fairly easily. So we have the square root of 32.2 times 8.74 cubed. And we get a value of, well, this 8.74 is actually incorrect. That's for a different part of this problem. So this 8.74 should actually be 7.60. And then we would replace that here, 7.60. Yeah, there we go. Okay, sorry about that. So anyways, once we calculate that, we get a unit discharge of 119 cubic feet per second per foot. And then we have an equation relating q, little q, which is the unit discharge, and the and little b, which is the total width of the bottom of the channel. And that's given right here, just q equals big Q over b. So we have q equals big Q over little b And so we can plug 119 into there. We know big Q from part A is 2940. And then little b is there, and we just calculate that. So little b is going to end up being 24.7 feet. And then we have part B completed, and that's what it was asking for, is the minimum width of the box culvert. So there we have it. Alright, moving on to part C. Part C, we have these two equations here. The top one is, again, just a manipulation of the Froude number equal 1 equation, and the bottom one is the specific energy equation, the general case of the specific energy equation. So for part C, we're given that B2 is equal to 20 feet in this part, and we're trying to find Y2 and Y1. Again, we're assuming that at section 2 right here, that is the critical depth. So let's draw a line here. So we can kind of reverse engineer the very last part of this, of part B. So if we have B here and we know it to be 20 feet now, we can multiply that times the discharge, or sorry, take the discharge and divide it by that number, and then we can get little q. We can find little q to get the Y2 critical. So we're basically working part B completely backwards. So we have little q is equal to big Q over little b, and big Q is not changing, and the little b is what's changing, and we're given it as 20 in this problem, or in this part of the problem. So we have Q is equal to 147 CFS per foot. And then from that we can find Y critical, and that is this equation up here, right here. That's just, again, another manipulation of the Froude number equal 1 equation, because we know at section 2 that the critical depth is the depth at section 2. So we have Y is equal to, and this is Y2, and that's equal to little q over g, it's q squared over little g to the 1/3 power. And we have little q, and we have 32.2 for g, all to the 1/3 power, and we calculate that to be 8.74 feet. Okay, so that's, we know the depth at section 2, which is part of what problem C is asking. Now we need to find the depth at section 1, and this is where the specific energy equation comes into play. So we have E1 equals Y1 plus Q squared over 2G A squared. That's the area of 1. And this is where we're going to have to do the iterative solution. This is going to end up being Y1 plus Q squared, which is 2940 squared, over 2G. And then the area is what gets a little bit difficult. This is where we're going to have to put the area in terms of Y1, the area of the trapezoidal channel in terms of Y1, and that's going to be 25 times Y1 plus 2 times Y1 squared, and all that squared because it's area squared. This right here, this number, is just something that you have to know how to calculate. I'm not going to go through that. That's in another video of how to put the area and the wood perimeter in terms of Y naught. So we have this equation here, and you're just going to have to solve that for Y1. That ends up being Y1 is equal to 15.13 feet. This is just a trial and error type of situation. You have to keep going through it. Oh, sorry, I forgot one step. So in order to solve this iterative solution, we need to know the value of E1. And in order to do that, we use the same equation as we did right here in part B, the 1.5 plus the K entrance over 2 times Y2 critical, again plus delta Z, but since we don't have a bed rise or bed drop, then that's irrelevant in this problem. And we know YC and we know the entrance loss, so we can find E1, and that's going to end up being 15.3 feet. So then you can set these two right here equal to each other and solve them. So yeah, then you would end up getting 15.13 feet for Y1. And that is part C completed. We have Y2 and Y1. That's what the problem is asking. Now finally we're going to ask what the bed drop needs to be in order to prevent a choke. So this is where this delta Z right here comes into play, because we're talking about a bed rise or a bed drop. So for this question, we just copy that equation down. We have E1 is equal to this 1.5 plus the entrance loss coefficient over 2 times Y2 critical plus delta Z. We know E1 to be 13.3 plus this is going to end up being 1.75 times Y2, which is 8.74 plus delta Z. And then this is simple, you just subtract this number over here and we end up getting a value for delta Z to be -2, and that all that means, the negative sign, all that means is it's a 2-foot drop in the bed. So these questions right here are pretty tough. Hopefully this video is going to help you guys understand how to work through these problems. All these equations should be on your equation sheet, so just remember how to use them. Always know that if you're given an n value here, you're always going to use Manning's equation. It's never just going to be thrown at you and trying to trick you. Always know how to calculate the geometry of a trapezoidal channel, whether that be the area or the wetted perimeter, and make sure you can do that in terms of y instead of just using the numbers. I know that's a lot harder, but yeah, make sure you know how to do that. The specific energy, know when to apply which equation, because there's going to be multiple forms of that on your equation sheet. Just know when to use which version. Same with the Froude number equation. Froude number equals 1 at the critical section, so make sure that you know how to manipulate that in order to find these different values of little q, g, and y critical. Know that little q is the discharge per unit area, or unit discharge, so that's just the discharge divided by the bed width. But yeah, hopefully these little tips helped. Good luck on your final. Hopefully this helped with you guys.